AI didn't kill the craft. It exposed it.
That is exactly right.
Yeah, that is the core thesis from Mirek Stanek's work, The Renaissance Engineer. And for you, the senior engineer trying to navigate an industry that is undergoing this massive tectonic shift, I really think it is the most critical realization you can make right now.
Absolutely.
Because we are entering an era where AI makes code incredibly abundant. Generating syntax? Well, it's just no longer the bottleneck.
Not at all.
Right, but what that sudden abundance does is it strips away the busy work. It exposes the true underlying fundamentals of the engineering craft, things like systems, precision, and radical ownership.
Yes, and that is exactly why we're looking at this today.
Exactly. So the mission of this deep dive is to synthesize Stanek's modern engineering pillars with Peter Senge's foundational concepts from his book, The Fifth Discipline Fieldbook. We want to provide you with a survival strategy for a landscape where typing code is cheap, but systemic understanding is invaluable.
It's a vital synthesis, honestly, for anyone building software today. Because when you look closely at Stanek's vision of this Renaissance engineer, you realize he is describing the exact type of professional required to build what Peter Senge defined decades ago as a learning organization.
Right.
Senge's whole premise was that an organization's true leverage doesn't lie in its budgets or its org charts. It lies in how its members think, how they interact, and how they adapt to complexity.
Which is more relevant now than ever.
Exactly. As the mechanical act of coding is increasingly offloaded to artificial intelligence, your primary value as a human engineer shifts almost entirely to those cognitive and interactive domains that Senge mapped out.
Okay, let's unpack this, starting with Stanek's observation that systems thinking must become the default engineering posture. Because he points out this really fascinating paradox taking hold right now. AI adoption is actually slowing some teams down.
Which sounds completely counterintuitive.
Right. On an individual level, output drastically increases. You might be generating features faster than you ever have in your career, but paradoxically, the coordination overhead increases even faster.
Yeah.
The system essentially bogs down under the weight of its own localized efficiency. But hold on, if I'm a senior dev and I can suddenly write boilerplate in 10 seconds instead of 10 minutes, how does that actually become a bottleneck?
What's fascinating here is how perfectly that maps to Senge's language of systems thinking. In system dynamics, what you are describing is known as a balancing loop.
A balancing loop.
Right. When you optimize only a single component of a complex system.
Individual code generation speed.
Exactly. When you only optimize that, the overarching system compensates elsewhere. It pushes back. The localized acceleration in your text editor creates immense, sudden stress on the integration, testing, security review, and deployment phases.
So the pipeline just chokes.
Yes, the balancing loop pushes back against your isolated growth, creating massive coordination bottlenecks. It's a classic example of how pushing harder on a single lever without understanding the whole system actually degrades overall performance. You aren't shipping a product faster. You're just piling up pull requests faster.
That makes a lot of sense. You know, Senge has this famous story about a puddle of oil in a factory to explain this exact difference between looking at an isolated event versus the whole system.
The 5 whys.
Right. Walk me through that and how it actually applies to a team shipping AI-generated code today.
Well, imagine a manufacturing plant. A foreman is walking the floor and sees a puddle of oil. In an event-oriented mindset, the foreman just yells at the nearest worker to clean it up.
And the problem is solved.
Quote-unquote solved, right.
Yeah.
But a systems thinker asks why the oil is there. The first why reveals a leaking gasket. The second why reveals that the mechanic installed defective gaskets.
It goes deeper.
It always does. The third why reveals that purchasing bought a batch of cheap gaskets to save money. And the final whys reveal a systemic root cause. An incentive structure that rewards procurement for cost cutting, completely divorced from the downstream costs of maintenance and safety.
Right, so let's translate that puddle of oil into a modern engineering reality.
Dang.
Let's say that puddle of oil is a massive memory leak that just took down your production environment.
Perfect example. And in an event-oriented mindset, your team just rolls back the deployment or restarts the pods. Problem solved.
We've all been there.
We have. But if you apply Senge's systemic lens to Stanek's software context, you have to start asking why. Why the memory leak? Well, because an engineer used AI to instantly generate a complex microservice, and the AI hallucinated a fragile dependency.
Why did the engineer push it without validating the dependency?
Because they were rushing to meet a sprint goal.
Why the rush?
Because the organization rewards teams entirely for feature velocity, with zero incentives tied to reliability or maintainability.
So the production incident isn't a technical problem at all.
It is a system design outcome. As a senior engineer, your job is no longer just to review the architecture. It is to map those incentives. You have to look for the second-order effects.
Because if the system rewards speed and punishes caution,
Then AI will just help your team build a fragile system much, much faster. You must ask what behavior your current process rewards and where critical feedback arrives too late.
which brings up the next crucial point. Because AI accelerates execution to such an extreme degree, the real risk to your project is no longer moving too slowly. The real risk is moving confidently in the wrong direction.
Yes.
Is shipping before you understand the user, or optimizing before validating the problem, or automating a process before questioning if the process should even exist in the first place. That's why Stanek argues that curiosity is no longer just a nice personality trait. It's operational hygiene.
It is the only way to avoid building the wrong thing at light speed. And this connects deeply to Senge's discipline of personal mastery. Senge argued that true mastery isn't just about producing results. It is about mastering the underlying principles of how you produce those results.
How does he frame that?
He uses the concept of creative tension. Imagine a rubber band stretched between your two hands. One hand represents your personal vision, what you truly want to create, the ideal architectural state.
Okay.
The other hand represents your current reality, the exact, unvarnished truth of where you are right now, bugs, tech debt, and all. The tension between those two hands is creative tension, and it naturally seeks resolution.
So if I just generate code with an LLM to blindly hit a Jira ticket without actually understanding the constraints or the user problem, I'm dropping the current reality hand.
Not just dropping it, you are pretending the bottom hand doesn't exist. You are letting the AI hallucinate a reality for you. When engineers lose that creative tension, they stop acting as architects of the future and become mere mechanics of the present.
That's a great way to put it.
Personal mastery requires the discipline to hold that rubber band taut. It requires you to delay the gratification of instantly generating code until your curiosity has fully mapped the reality of the problem space.
And without that tension, you end up with the engineering waste Stanek describes. You operate out of a reactive orientation where you just putting out fires. Or in our case, debugging AI-generated spaghetti code, rather than a creative orientation where you are intentionally building toward a vision.
That is the core danger of code abundance. If you don't enforce curiosity as a discipline, the abundance of code just becomes an abundance of liability.
Here's where it gets really interesting. Let's talk about communication and ambiguity. Stanek states that in an AI-augmented environment, ambiguity is technical debt. He calls for precision communication as vital infrastructure.
Yes, vital infrastructure.
Why?
Yeah.
Because AI reads the lines. It does not read between the lines. If you give an LLM garbage constraints, it doesn't push back to clarify your political context. It just returns incredibly convincing, articulate garbage.
It sounds so certain while being entirely wrong.
Exactly. I actually lived this last week. I spent 3 hours debugging a script because the LLM confidently imported a perfectly named, highly logical library that simply did not exist.
Yeah.
It assumed my vague prompt meant I wanted a specific utility, and it just invented it.
That is a perfect illustration. And this is where Senge's discipline of mental models becomes a survival tool. Human beings, especially in complex engineering organizations, operate on what Senge calls a ladder of inference.
A ladder of inference.
Right. At the bottom of the ladder is observable data. But very quickly, we climb up the rungs, we add cultural meaning, we make assumptions, we draw conclusions, and finally, we take action based on deeply ingrained, hidden mental models.
And humans naturally read those models in each other.
Yes, when humans communicate with other humans, we unconsciously navigate each other's ladders. AI cannot do this.
So we need to explicitly walk up that ladder. Let's ground this. Give me a real engineering example of how this breaks down with AI if we don't manage our mental models.
Let's say you are using GitHub Copilot to write a new microservice. At the bottom of the ladder, the observable data. The AI generates a caching layer for user profiles. Now, let's climb rung 1. The human engineer assumes this cache needs a standard 5-minute time to live based on past projects.
Makes sense.
Run 2, the engineer assumes the security team doesn't need to review this because historically it's just a cache. Rung 3, the engineer assumes the architecture board wants this shipped today because the executive directive was to make it fast.
But when an executive says, make it fast, the hidden mental model might actually be, make it cheap because we're running out of runway. Or when a manager says, ship it, the unstated context on their ladder of inference is, ship it so I can cover my political risk for this quarter.
Precisely. And in our scenario, the engineer deploys that caching layer based on all those hidden assumptions. The result? A massive data leak because the AI-generated cache bypassed the company's new authentication middleware.
Because the AI didn't know the undocumented security models.
It didn't know the political pressure, it just executed the observable data efficiently. Therefore, to survive and leverage AI effectively, you must make these mental models visible and explicit.
It's no longer a soft skill. It's infrastructure.
It is the fundamental infrastructure of your code base. If your prompt engineering or system constraints contain hidden assumptions, the AI will build a system optimized for a reality that doesn't exist. Precision communication, learning to explicitly state the bottom rungs of your ladder of inference, becomes the only way to prevent the system from generating highly efficient, automated disasters.
But making those mental models visible is risky, right? Stanek brings up the concept of radical ownership, borrowing the Andon cord from Toyota's manufacturing plants. He argues that any engineer should be able to pause a deployment, escalate a risk, or block a release without facing any social penalty.
Right, pull the cord and stop the line.
Exactly. His point is blunt. If escalation is culturally risky, problems hide until they explode. But let's be real. If an engineer pulls the Andon cord to call out a toxic incentive, or stops a massive AI-generated release because it violates an undocumented mental model, they usually get penalized. How does an organization actually support this level of radical ownership?
This raises an important question, because it is easy to tell an engineer they own the release, but it is another thing entirely to make it safe to halt one. Senge addresses this through what he calls the architecture of learning organizations. He visualizes this architecture as a triangle.
What are the points?
The 3 points are guiding ideas, theory methods and tools, and innovations in infrastructure.
And in tech, people usually obsess over the tools, right?
Yeah.
We buy the new software, we implement the new Agile framework, we buy enterprise Copilot licenses, but nothing fundamentally changes about the culture.
Yes, because they ignore the innovations in infrastructure point of the triangle. And to be clear, for a Renaissance engineer, infrastructure isn't just your AWS servers or your CI/CD pipeline. It is the social architecture of the company.
The human systems.
Exactly. It is the reward systems, the performance reviews, the management support, and the psychological safety that makes pulling the Andon cord a celebrated act rather than a career-limiting move.
So in plain English, your company needs to make it completely safe for a junior dev to look at the VP of engineering and say, your new AI feature is going to take down the production database, so I block the deployment.
That is exactly what it means. Senge warns that re-engineering efforts consistently fail when they attack structural tools without changing the social infrastructure. Radical ownership requires an architecture where loyalty to the truth supersedes loyalty to the hierarchy.
Because if you don't have that,
If you don't have that social infrastructure, AI will just help your organization make terrible systemic mistakes much faster because everyone will be too afraid to stop the automated assembly line.
that structural perspective is vital, and it perfectly sets up Stanek's final pillar, polymethy as leverage. He makes the point that narrow specialization is exactly what AI handles perfectly. It can write a specific sorting algorithm, or optimize a database query, or write a reject string faster than any human alive.
It's unbeatable in a narrow scope.
Therefore, your human advantage entirely shifts toward integration. It shifts toward context interpretation and navigating complex trade-offs. To do that, engineers must understand how product decisions are made. They have to understand how cost structures shape cloud architecture.
Senge frames this through the disciplines of team learning and shared vision. It is crucial to remember that great teams rarely start off as great. They develop the capability to work as a unified whole over time. When an engineer intentionally builds adjacent domain literacy, when they learn the language of finance or the constraints of the UX design team, they are actively dissolving what Senge calls the organizational stovepipes. These are the rigid functional subspecialties that keep organizations fragmented.
So polymathy isn't about being a hobbyist in 5 different fields. It's about building the connective tissue between those stovepipes. It's about being the person who can look at the AI-generated code and say, yes, this is technically efficient, but it's going to ruin our AWS bill. Or, yes, this works, but it completely violates the user journey the design team mapped out.
Think about it like this. The Renaissance engineer engages in Senja's deep learning cycle. This isn't just about shifting skills, it is about fundamentally shifting awareness and attitudes.
Evolving how you see the business.
Yes.
Yeah.
When you sit alongside a product manager and truly learn how they weigh customer feedback, or sit with a finance expert and learn how capital expenditure impacts technical debt, your mental models evolve. You stop being a localized code generator and become a systemic integrator. You develop the shared meaning necessary to align AI's massive output with the actual destiny of the organization.
So what does this all mean? Let's synthesize everything we've covered today. As AI makes the raw generation of code abundant and cheap, the software engineering craft is not dying. It is returning to its roots. The survival strategy for you as a senior engineer is to aggressively merge Stanic's modern fundamentals with Senja's enduring disciplines.
Perfect synthesis.
You must view curiosity as operational hygiene, driving your personal mastery so you don't build the wrong thing. You must adopt systems thinking to manage the balancing loops of AI coordination and look past the puddle of oil to the root incentives. You must practice precision communication to expose hidden mental models before they become automated disasters.
Absolutely.
You must demand the social infrastructure that allows for radical ownership, where anyone can pull the anon cord. And you must cultivate polymathy to facilitate true team learning and dissolve organizational stovepipes. It is no longer about what specific syntax you know. It is about what you keep learning, how you connect the broader system, and what you choose to take ultimate responsibility for.
I want to leave you with a final lingering thought to explore, drawn directly from Senja's work on microworlds and management flight simulators.
Okay.
In the Fieldbook, Senj describes microworlds as practice fields. They are simulated environments where management teams can test their assumptions, compress time, and safely witness the systemic consequences of their actions over years without actually bankrupting the company. Historically, these took months of painstaking programming to build.
Sure.
But consider the reality Stanic has presented. AI can now instantly generate and execute code. Perhaps the future of software engineering isn't about building the final product at all. Instead, it is about Renaissance engineers using AI to instantly spin up infinite, highly detailed microworlds.
Wait, so instead of building the app, we build a simulation of the app and a simulation of the users and the market, just to see if the architecture even survives contact with reality before we write a single line of production code?
Precisely. You could turn the entire job of engineering into designing continuous systemic experiments. You would be testing hypotheses, mapping those second-order effects we talked about, and adjusting incentive structures in real time within the simulation, rather than manually writing the software that runs the business. The code itself becomes disposable. The systemic insights become the product.
A profound shift from writing instructions to designing systemic experiments. Take that thought and look at your own systems differently tomorrow.